Olivia, president of Build and Launch Team 6352. In the midst of our water game season at our Waterworks facility, we've done a lot of work with motors to prep for competition. But with motors comes gear ratios, and although most of us don't like to admit it, many of us don't understand how gear ratios work or how to calculate them or how to use them. So today we'll be going over the thought process behind how to use these gear ratios and calculate them, and hopefully this will help you in your robot building process. First off, what is a gear ratio? Gear ratios are differences in gear sizes that allow for changes in a motor's output. They allow for changes in torque, which can change the speed of the motor, and allow smaller motors to complete larger tasks. Think of a gear ratio as a lever arm. To move the item on one side, you need enough force on the other. But if you increase the length of that lever arm, the amount of force needed decreases. But that also increases the amount of distance you have to move the lever arm in order to move the item. So that distance is smaller than the distance of the increased lever arm. This is essentially what your gear ratio does. It decreases the amount of force required while increasing the motor's available output. You can adjust the speed once you have enough torque. When calculating gear ratios, there are a few things you need to know beforehand. Number one, the application. Where will the motor be used? Will it be used on a linear actuator, an elevator, or drive base? Number two, the weight. Knowing where your motor will be used allows you to guess the weight of your object. Is it a 100-pound element like a robot or a 10-pound elevator? You don't need specifics, but considering your objects in terms of the order of magnitude, otherwise known as the Fermi estimation, should be sufficient. Number three, the motor type. What kinds of motors are you planning on using? The possible outputs of the motor depend on which motors you're planning on using, such as Krakens, Neos, or servos. 4. The speed. It's good to have a general idea of how fast the object needs to move to complete the task. Does it have to speed across a field or just lift up slowly to deliver coral? For example, let's look at our elevator. We like to think about our elevator the same way we consider our drive base. The output for both is a spinning wheel or shaft, whether it's a 4-inch Coulson or a 2-inch sprocket. In both contexts, the axle has to rotate tens of times to complete its task of either lifting the elevator up or driving the robot forward. You want to consider the torque needed. Luckily, there are many resources online to help with this, such as motors.vex.com and AndyMark. Charts and graphs of motor performance can help you decide what ratio is best to use on your bot. Let's take a look at this one from Vex Motors. For motors, it's generally best to choose a range within peak power and peak efficiency. Based on the chart, you can view how much current you'd end up using and how much torque would be available. Is that enough torque to complete your task? You might have to change motors if that range isn't sufficient. Within that range of availability, you can use a gear ratio to change the torque output of that motor. This chart on AndyMark shows gear ratios and speed in relation to the torque. Since you now know the torque, you can choose the gear ratio and the speed needed for your motor. On the chart here, lower numerics, such as 5.95 to 1 and 7.31 to 1, mean that there is a higher ratio, so there is less torque. That means they're used for lighter, easier to lift objects. Higher numerics, such as 10.71 to 1 and even 100 to 1, are lower ratios, so result in more torque to use for heavier, harder to lift objects. And that's basically it. Now that you understand gear ratios, you should be ready for takeoff. We'll see you at competition.